Hello guys, welcome to the lesson. After so many problems in the last week, let's uh, let's actually review the whole thing. Even though maybe we spoke some things about this, I want to redo the whole thing on video because as we could see last week, probably a lot of these things were not understood by most of you, given the problems of the echo in the classroom, etc. So let's begin. In this chapter number 7, we're going to study statistics for bivariate data. And let's introduce the chapter by making a brief refreshing of what we studied in the previous chapter, chapter number 6. In there, we studied univariate analysis, and that was a study of one variable obtained from a set of individuals or objects of study. Remember, guys, that what we are doing when we do statistics is we have some individuals or some objects. We can call them in these two ways, okay? And they may be people, okay? They may be people or they may be cars, right? Or they may be dogs or any other set of objects. It's irrelevant. And we want to study one variable from these particular individuals, right? From the case of people, sometimes we study the weight of these people or the height of these people or the scores of these people in some exam, etc. For the car, I can study the mass of the car or maybe its efficiency, its fuel efficiency, something like that. But each of these things is just a variable, right? In univariate analysis, when we studied a variable from a specific set of objects, it was just one variable, either the weight or the height or the scores, etc. But we never considered any two or more variables of study at the same time. That's what is known as univariate analysis, and that's what we did in the previous chapter. That's all we did. And what kind of study did we do? Well, we studied, for example, how to get measures of central tendency, if you remember, such as the mean, the median, the mode, etc. And also some measures of dispersion, right? Measures of dispersion, such as the quartiles, the standard deviation, um, the interquartile range, etc. Okay, and all of these things give us a good picture, a good picture of the analyzed set of numbers, the analyzed data set. I give you a picture, what for? So that we can make interpretations for any given problem, right? Whether in the industry or anywhere, it doesn't matter. That's why we want to do univariate analysis and come up with all of these quantities. Okay, that was univariate analysis. And basically everything that I've told you right here is basically all of this. Okay, so I don't really need to go over each of these examples. Maybe just the first one. Look at this. My objects of study is a set of five people. I choose five people to analyze. Those are my objects. Now, what variable am I gonna observe about these objects? Well, maybe I want to observe the height of these five people in centimeters. Okay, perfect. Then I do the measuring, I do the observations, and after that I come up with my data set, mi conjunto de datos, which could look something like this, right? These are the five heights of these five people. That's basically what we did in univariate analysis. And then after this, we can calculate mean, mode, median, standard deviation, blah blah blah, uh, the histograms, etc. Okay, that's what we did. Okay, so now what is bivariate analysis? I was telling you that what the book says is this. It provides only a very vague, in my opinion, very vague, very simple-minded definition of what bivariate data analysis is. and they tell you that it's the study of the relationship between two data sets. This is way, way too general, extremely general. And so I can conclude that something is lacking in this definition. Maybe not something, but some things. Some things are lacking. Okay? Try to remember this definition. Bivariate data analysis is a study of the relationship between two data sets. And I'm going to tell you why that's a little or a lot, yeah, inconvenient as a definition. Well, let me tell you right here. I told you that one of the criticisms that I can provide for this explanation is that when they tell you this, they never make explicit the idea that those two data sets, in the first place, they have to be of the same size, right? For example, if this is the weight of three objects and this is the height of those same three objects, then they have to be of the same size, guys. These sets have to be of the same size, something which this definition never makes mention to. Okay, it never makes any mention to the size. Also, in this definition, there never is any sense of correspondence or matching between which values in the datasets are corresponding values. For example, this weight, this weight, which is the height, which of these three is the height corresponding to this weight? Is it going to be the first one? The definition never says so. You see, it never makes explicit that fact. So there is no sense of correspondence or matching in this definition, and therefore, in my opinion, it is very lacking, extremely lacking, in my opinion. So, what is bivariate analysis then? Okay, let's see what I wrote for you. Bivariate analysis is the analysis of a data set. First of all, we have a data set. What that means is that we have something like this, a set that contains data inside. Okay, that's a data set. What type of data does it have? Let's read. Is the analysis of a data set in which each of these values, let's imagine that we have 5 values in my data set. Each value consists of a couple of observations from each individual. You see, a couple of observations from each individual. Each observation represents a variable, and the notion of correspondence or matching should be made explicit. For a particular value of the first variable, there corresponds a specific value of the second one. In short, our datasets in bivariate analysis will consist of a set of points of two coordinates. It's a set of points of two coordinates, so it's gonna look something like this, like this. Okay, it's a set which has points of two coordinates as its values. We have the first value in my data set, the second value, the third value, the fourth value, and the fifth value, and each of those values is a point of two coordinates. Now, what does each coordinate represent? It represents both variables that I'm analyzing. The first representing the first variable, whatever variable I'm talking about, and the second point, the second coordinate representing the second variable. And thus, when we define bivariate analysis in this way, guys, in this particular way, then there is no ambiguity because I'm basically telling you, let me erase this. I'm basically telling you that the idea of correspondence is very important. Okay, these two values correspond to each other. Okay, if once again, if we think of this as the weight of something and this as the height of something, then this height corresponds to this particular weight for this particular object. This is the couple of observations made from the same object. Let's say a cat. Okay, we are analyzing 5 cats. These are the heights. I'm sorry, these are the weights and these are the heights. Then we can see that this point This data point represents the observations made from a particular cat1. Okay, and this data point corresponds to a couple of observations of weight and height to, let's say, cat2, and for these are for the cat3, cat4, and cat5. In this way, there is no longer any sense of ambiguity in this definition. Of course, it's much longer than the previous one, but it's necessary. It's necessary to explain with precision what we are doing and what our concepts mean. It's extremely important as mathematicians. Let's analyze this study, this example. I'm sorry. Objects of study. What do I want to analyze? 20 students from the IB class. What variables am I interested in studying? Well, maybe the midterm exam score. That's one variable. It's quantifiable, right? As an integer from 0 to 100. And versus what other variable? The number of hours slept the night before the exam. Also quantifiable, okay? And thus, we can have, after we do the analysis or the observations, we can come up with a data set that looks like this, okay? Each of these points, and this, each of these points is a value in the data set, also known as a data point. This is a data point of my data set. This is the second data point. This is the third data point, etc. And each data point consists of two observations. In order, the score and the number of hours slept the night before by this particular individual. This individual that got 78 on the score on the exam slept 6 hours. This other individual that got 90 on the exam slept 7.5 hours, etc., etc. You see, in this, with this whole explanation now, there is no sense of ambiguity as to what we are referring to when we talk about bivariate analysis. I want to skip this one. So now, what is a scatter diagram? Now let's go into the first subtopic, 7.1, scatter diagrams, diagramos de dispersión en español. A scatter diagram is a diagram in the Cartesian plane that depicts each of the data points of a data set of bivariate data. So suppose we're working with bivariate data. For example, in this example given by the book, these are your objects of study, 10 students. You're analyzing the height and the weight, so that is a couple of observations for each of these 10 students, and you are writing down the observations by means of a table, like so, height and weight. And I mean, the book doesn't tell you so, but I mean, it's clear that in this case, my data set consists of the following data points: 182,90. So that is the height and the weight of the first individual. This couple of observations, and then this other couple, 155,60, and so on for the rest. So each of these data points can be plotted on a Cartesian plane in this way. 182,90, that's this point. 155,60, that is this point. No, this point, etc. So we do the same for each of the data points of my data set, and that representation is what is known as a scatter diagram. Okay, it's basically the graph of the data set. Now, let's talk about the concept of correlation. In the meantime, in this subtopic 7.1, guys, we're going to talk about correlation and causation and many other ideas in pretty vague terms. Okay, just the concept, not the number crunching parts. Okay, not the formal definitions. So let's see what this means. The concept of correlation between two variables x and y is the degree the degree to which they are statistically related. Okay, this relationship between these two variables may be causal or not. Pay attention to the word. Don't confuse it with casual, because that's kind of like, uh, I mean, it would be very easy to confuse these two words, right? Casual and causal, causal, causal. This relationship may be causal or not. For example, in this case of the 10 students measuring their heights and their weights, we can observe this diagram, and there seems to be some sort of relationship, right? Okay, what kind of relationship? The higher the greater the height, the greater the weight, right? Okay, now in this case, given our understanding of the world, there is causation, right? Because the more height you have, the more mass you're gonna put on in your body, right? I mean, you have more bone, more organs, or if they're larger, and thus the weight is correlated strongly with height. And there is the concept of causation, although we're gonna take a look at that in a moment. But the fact that we can see this type of relationship or this type of correlation does not necessarily mean that there is causation behind it. Not necessarily. We're gonna analyze these ideas in due time. We can describe a correlation between two variables with three properties: positive or negative. Correlation can be either positive or negative, strong or weak, and linear or nonlinear. Positive or negative. Look at this image. In here we have negative correlation for this scatter diagram, and for this other scatter diagram we have positive correlation. So how can I understand the difference between negative and positive correlation? Well, for negative correlation, if we think of variables x and y, then basically what we are saying, when we say that x and y are negatively correlated, that means that the greater the x, the less the y. And when we say that x and y are positively correlated, what that means is that the greater the x, the greater the y. That's, in a nutshell, that's what it is, conceptually speaking. Conceptually speaking. Now, strong or weak. Look at these six scatter diagrams. For example, in this one, in 1 and 2, we can observe positive correlation, but we can observe that in here, the points are very close. They are very close to a straight line. You see, and that's what we mean by strong positive correlation. And when they depart uh, more than in this previous case, when they depart, I mean, they follow closely also this line, but not as much as these ones. You see, they don't fall that much into the straight line. What we say it's that's a weak positive correlation, or even we can think of a moderate correlation, such as this. Okay, this is not as good a correlation as this, but it's also moderate. Okay, it's just moderate. So moderate, strong, or weak. That's the way you can understand this. It's basically how close the points in the scatter diagram are to a specific straight line. And now for this, for linear or nonlinear, basically for linear correlation, the points get closer, lay close to a straight line, and for nonlinear, which is this case, this is nonlinear correlation, the points basically follow the path of something that is not a straight line, such as this, right? A parabola or something else. Now, what about the concept of causation? Let's address this thing. The concept of causation revolves around the idea of there being a causal relationship between a variable x and a variable y. X causing y. Let's look at some examples. Take a look at this. The distance d from a constant source of heat to a glass of water. will cause a change in the temperature T of the water. For example, if I have on a table, I have some water in here in some glass, and maybe I have a source of heat. I don't know, it can be anything. It can be a light bulb or something. This is a source of heat. So in this system, what can I analyze? What two variables? Well, I can analyze the distance, d, from the heat source to the glass of water, and I can analyze also the temperature of the water. So these are my two variables, right? This is my system. This is my two variables, and I can play with this. I can put the heat source closer or farther away from this glass of water and observe how this changes. Now, will the temperature change? Yes, yes, we know that, right? So, is there a causation? In this case, there is, because given our understanding of physics, and I mean, for reasons that have to do with physics and the concept of causation, basically, uh, we can assess causation in this case. That means the following: whenever whenever d is less, the temperature will be higher. Okay, and that's a law of nature, and therefore we can assess causality basically. What about this one, the family income? Let's represent that variable through I. Family income, I for income, and the highest level of education of the children. Are these two variables causally connected? Yes, yes. As far as I understand the statistics, they do not only correlate. I mean, they obviously correlate, but there is a there is a causation behind that correlation. In what sense? Well, it's obvious that the more income the family produces or the family has, the more that, I mean, the greater education that they will be given to their offspring, right? In terms of better schools. Uh, I don't know, they buy more books to their children, they buy more computers, they have more access to those things that are necessary for a high level of education. Putting their kids through college, putting them through maybe a master, a PhD, etc., etc. So there is not only correlation, but there is some degree of causation. Maybe not perfect, maybe not absolute, but there is causation indeed. Now, what about this? The length of the side of a square. Let's imagine a square, and we have this S, which is the length of the side of the square. Let me put it here. And what other variable of interest can a square have? The area, right? All of this area. So we have these two variables, the side, the length of the side, and the area of the square. It's clear that if I change the length of the side, okay, S prime, A prime, because they are different, right? Then the area will also change. If S goes up, A goes up. If S goes down, A goes down. So there is obviously causation in this very particular example. Usually in mathematical examples like this, the concept of causation is, I mean, it's obvious. It's right in your face. So you don't have to think that much. In other examples such as this one, okay, examples of let's say real life, it is much more difficult to assess causation. It is in fact extremely difficult, to be honest with you. um, Let me stop right here, because as I was telling you, I don't want to dizzy you with so much video. Let's stop right here. We're going to continue with these slides uh, live, on a live discussion, which addresses the idea of how can we assess causation if we have correlation between two variables? That's an extremely important problem in science, and let's try to think a little about that. But I see you live. I want to stop the video right now. Thank you, guys.